My name is Ana Carolina Rios. I'm a master's student at the University of Brasília. My secondment took place at the École de Pont, Paris Tech, and my research regards the simulation of the black oil model with a finite element method. The black oil model is a compositional model very famous in the petroleum industry. The motivation of my work resides in the importance of reservoir simulation. A reservoir rock may contain up to three phases: water, gas, and oil, and phase changes may occur due to the pressure gradients, so they have to be accounted for in order to have a good estimation of production and also a good strategy of recovery that may include some secondary recovery techniques such as fluid injection and other special methods. Also, it is important to simulate the flow in this reservoir because it is associated to some major deformation events such as compaction, subsidence, fault reactivation, and induced seismicity. Now I'll give a brief contextualization on the use of the finite element methods in flow simulation. The finite element method was not until recently very popular in the field of modeling multi-compositional and multi-phase flows. That's mainly because the classical formulation is not locally conservative, what means that it doesn't obey to mass conservation within the elements. Also, the classical finite element method gives oscillatory results for convection-dominated problems, what makes it not suited for some cases of compressible flows. Despite all of that, the finite element method has the very appealing feature of allowing a flexible discretization. This is very attractive in reservoir simulation because reservoirs are very complex domains that may contain some important discontinuities. So for that reason, some developments were made in order to make the finite element method competitive in reservoir simulation. Some works focused on post-processing techniques that basically correct the results of the classical finite element method in order to make it locally conservative. Also, there are the Petrov-Galerkin methods that give some more realistic results for convection-dominated problems. Formulations of the finite element methods which are locally conservative arose, and the most famous one are the discontinuous Galerkin and the mixed finite element methods. They both became very popular in reservoir simulation, especially two-phase flow and the black oil model simulations. Also, some methods try to combine the best features of the finite element method and the finite volume method. An example of that is the very famous contour volume finite element method, and also combined methods that use the called IMPS, implicit pressure explicit saturation formulations for solving the pressure equation in finite element methods and the saturation equation in finite volume methods. So, the black oil model is used to mathematically describe the partial vaporization of the liquid hydrocarbonates in a reservoir. Is suited for low volatility reservoirs that contain initially only oil in the liquid phase with some dissolved gas. As production starts and pressure drops, part of this oil is going to vaporize into a free gas phase. So the system is made of three equations of conservation of mass, one for each of the components that are the gas component, the oil component, and the water component. And they can be distributed among three different phases. There's a liquid phase that initially contains all the dissolved gas, that is the gas component, and the dead oil component, that's the oil that doesn't vaporize under standard conditions. There's a gas phase that only appears after vaporization starts and it's entirely constituted by the gas component that was initially dissolved in oil. And there's the aqueous phase entirely composed by water and it doesn't make changes with the other ones. So in order to solve this mathematical model, some constitutive relations are required and they are a source of nonlinearities in the solution. There's a permeability curve as a function of saturation, and there's a viscosity described as a function of pressure, and they both form the property of transmissibility. Also, there's a capillary pressure curve that describes capillary pressure as a function of saturation. Capillary pressure is commonly ignored in reservoir models because it's very small when compared to pressures of the natural reservoir rock. There's a gas solubility ratio and the components volume formation factors as a function of pressure, and they are going to describe phase changes and the fluid's compressibility. It is also valid to mention 3 different mathematical approaches used to solve the black hole model. There's a full implicit formulation in which all the 3 equations are simultaneously solved. It is a very stable method, but may require a tremendous amount of computational sources, so it's not always efficient. There's the implicit pressure explicit saturation scheme that divides the problem in 3 different equations. There's the pressure equation that is solved implicitly, and there are 2 other equations that are solved explicitly. It's a way more efficient method, but it's not always stable. It's stable only for small time steps. So it's not always an advantage to use the implicit pressure explicit saturation, especially for the black hole model that is a very complex model. And there's a middle term between these 2 methods, that's the sequential method. It's an implicit formulation, but instead of solving all the equations simultaneously, it solves the equations sequentially. So it is more stable than the implicit pressure explicit saturation formulation and less stable than a fully implicit formulation, but it's more efficient than this one. Now I can present my research objectives. The main objective is to develop a finite element code to solve the black hole model and two-phase flow and apply the code in the simulation of a reservoir. Specific objectives are creating a standard finite element code to solve the black hole model and two-phase flow, and correcting it with post-processing techniques in order to make the formulation locally conservative. Implement a fully implicit finite element code with post-processing. Integrating a new modulus on an already existing program in the University of Brasilia, designated to simulate propagation of fractures. And use the developed code to analyze the efficiency of a secondary recovery technique. Here's the scope of the methodology that I'm going to use to develop the code. It will be implemented in 2 different modulus. The first modulus, designated to solution of two-phase flow, is going to be validated with the Buck-Leverett equation and the software Flex PDE. The second modulus, designated to black hole model simulation, is going to be validated with numerical examples by 2 different works, the works of Friendstorm and Ertekin and Bergamaschi et al., and also the software Flex PDE. The approach that I'm going to use is a fully implicit scheme of solution that will be carried out to a local conservation analysis with a control volume technique. If the error in conservation is beyond an estimated limit, it will be corrected with a Newton iterative method. The code is going to be applied in the simulation of a reservoir in order to simulate primary oil recovery and also to evaluate a secondary recovery technique, as for example, water injection. These are the references that I used throughout the presentation. I would like to thank you for your attention and clarify that there are still no results available because the code is still being developed, but soon there will be conclusions. Thank you.